Hey everyone, let's go over differential equations, some of these word problems from this worksheet. So let me read the problem here. At the beginning of 2010, a landfill containing 1,400 tons of solid waste. The increasing function W models the total amount of solid waste stored at the landfill. Planners estimate that W will satisfy the differential equation, dW dt equals 1/25 W minus 300 for the next 20 years. W is measured in tons and T is measured in years from the start of 2010. Okay, so part A says use a line tangent to the graph of W at T equals 0 to approximate the amount of solid waste that the landfill contains at the end of 3 months, which is T equals 1/4. So this is a linear approximation problem, but first we have to get to our tangent line. Okay, so to get to tangent line, we need to find order pair and we need to find slope. So I think something that we have to get used to is sometimes we may see equations where we're not dealing with x's and y's. So in this case, we're not dealing with x's and y's, but we should have to understand that instead of x and y, we're now dealing with order pair T and W. So we're going to treat T as our independent variable, and then W is our dependent variable. So we just have to kind of train our eyes to just to kind of make that adjustment, right? That variable T represents X, and then W is our basically our Y variable. Okay, so we need to find our order pair. So we know at T equals 0, the amount of waste is 1,400 tons, so we can treat that like the order pair. Okay, so that's going to be the first piece of information that we can gather from the problem. The next part is we need to find the slope, right? And to find the slope, we have to rely on the derivative, and the derivative, we're going to be plugging in the order pair 0, 1,400 into the derivative, and in return, we can get the slope. So there's no T for us to plug in, but we do have a W that we can enter in. So 1,400 in for W. So we can treat this like the Y, basically. Okay, whatever the the derivative equation requires. Okay, so we enter 0 and 1,400 into the derivative. There's no place for T, so only W is required. So 1,400 minus 300 divided by 25 gives us 44. Okay, so we have our order pair, we have our slope, and now we're going to put this into point slope form. Now, usually we think of point slope form as y minus y1 equals m times x minus x1, but instead of x and y's, we're dealing with t's and w's. So instead of y minus y1, we'll do w minus w1 equals m times t minus t1. We'll replace t and w with 0 and 1,400, just like how we would if we were dealing with x's and y's, and then replace slope with 44. And then here's our tangent line equation. Okay, let's solve for w. So we'll add 1,400 to both sides, and we get 44t plus 1,400. So here is our tangent line equation. And then the last part is we're going to approximate the amount of solid waste in the landfill by plugging in 1/4 into our tangent line equation. Okay, so think of this as our decimal value that we're entering in. So you can either put 0.25 or 1/4. Either way, we're taking a value and putting it into the linear equation to gather our approximation. So 1/4 goes in for T into our linear equation. In return, we get 44 times 1/4, which is 11, plus 1,400. We get 1,411 tons. Okay, part B, use the second derivative in terms of, or find the second derivative in terms of W. So we have the first derivative. We just want to make our way to the second derivative. Okay. And then after we find that, it says use the second derivative to determine whether our answer in part A is an underestimate or an overestimate of the amount of solid waste that the landfill contains at time t equals 1/4. So let's go ahead and try to find the second derivative. Okay, so we can think of dw dt. If it helps, we can think of dw dt. If we distribute this through as 1/25 w minus 1/25 of 300. Okay, and if I want to find the derivative, right, dw dt will become d2 w over dt2. That just indicates that I'm finding the second derivative. And 1/25 w, we know that w will turn itself into dw dt. 1/25 is just going to tag along. But here, this is going to just become 0, right? So our second derivative is just going to be 1/25 dw dt. Okay, because w becomes w prime, which we represent as dw dt. So if this is the second derivative equation, then we can make some progress because we know dw dt, if we go back to the original problem, it's just 1/25 parentheses w minus 300. So if I replace dw dt with my original problem, and now I have the second derivative in terms of w. Okay, 1/25 times 1/25 becomes 1/625 times w minus 300. Okay, now we know that w starts at 1400, right? We know that at the beginning of 2010, the landfill already has 1,400 tons of waste. So we know that no matter what our value is after 1,400, there's no way that this value can ever be negative. So we know that the second derivative, no matter what, is always going to be positive. And because our second derivative, our function is positive, that means the graph is concave up. If the graph is concave up, that means the graph looks like this. If the graph looks like this, we know that any tangent line to a concave up graph will end up underestimating a point on the curve. So we know the tangent line is an underestimation. All right, part C says find the particular solution for w equals wt to the differential equation with initial condition w of 0 equals 1400. All right, so we're going to solve the differential equation. The first thing I like to do is cross multiply. So, but I'm going to put that 25 below w minus 300. And once I'm here, I can do cross product. So I'll multiply the diagonals with each other. So I get 25 times dw is equal to w minus 300 dt. Okay. Now I know that maybe with differential equations, we're used to x's on the right and y's on the left. But in this case, instead of x's and y's, we have t being the independent variable and w being the dependent variable. So we want w on the left side like we would if we had y's in the equation. And instead of x's on the right, we're going to try to combine all the variable t's together on the right side. Okay. All right, so we do have a couple of things out of place. The w minus 300 needs to be over here on the left side, so we'll divide the w minus 300 over. The 25 is not it's not wrong if we have it on the left side, but anytime that we can leave the left side as minimal as possible, I think it helps. So I'm going to divide the 25 over to the right side at the same time. So the w minus 300 is going to shift to the left in the denominator, and the 25 is going to divide over to the right side. So now we have dw over w minus 300 over dt over 25. So now we have full separation of variables. W is on the left, everything else on the right. So we can take the antiderivative. We know that this side is going to require a little bit of u substitution. That w minus 300 is a little messy, where we can't just jump into an integral rule. So we'll let u equal W minus 300, du equals dw, d over dw equals 1, du equals dw. So it looks like there's no coefficient that we have to keep track of. This is simply going to be a natural log problem. So du over u. Okay. Equals, and we know that eventually we can apply power rule. If I push that 1 over 25th out, we know eventually that's going to become t. So we're going to apply power rule on the right side, natural log on the left. So 1 over u du becomes natural log absolute value of u equals 1 over 25th. Integral of 1 becomes t, and then we include the plus c on the right side. Okay. All right, we have the antiderivative. We're going to bring the u back in terms of the original variable. So replace u with w minus 300. All right, so I would like to solve for w first, because I know that if I can raise both sides with e as the base, this will clean up nicely, and then that c is going to absorb a bunch of messiness here. So I'm going to raise both sides with e as the base. E to the natural log, that's just going to go away, leaving me with just w minus 300. E to the 1 over 25th plus c, I can split up into e to the 1/25th t times e to the c. We know what happens with e to the c. E to the c is just a constant, and that constant is just going to be a times c, and that c we can move out in front. If we drop the absolute value bar, we're going to end up with a plus or minus c, and then plus or minus c, we can just let it absorb into just a c here. So, okay, so this cleans up nicely, right? We got rid of the natural log. We're able to drop the absolute value. We got the c to absorb the plus or minus. And now I'm going to solve for w. Just move that 300 over. And when I move that 300 over, now I have a pretty clean general equation. And now I'll have an easier time finding the c value. There's less messiness to deal with now. So I'll plug in 0, 1400, 0 in for t, 1400 in for w, and that will allow me to solve for c. So 1400 goes in for w, 0 goes in for t. E to the 0 is just going to be 1. So I have 1400 equals c plus 300. We subtract 300 from both sides. C equals 1100. And once we have our c value, we can update our general equation and move it up to a specific solution. Okay, replace c with 1100. There's our answer. Okay, all right, let's go to the problem on the back here, number 2. All right, solutions to the differential equation. Dy dx equals xy cubed satisfies the second derivative. So they already found the second derivative equation for us, and this is going to be our starting point. Let y equals f of x be a particular solution to the differential equation with f of 1 equals 2. Part A says write an equation for the line tangent to the curve to the graph of y equals f of x at x equals 1. So now we're back to more familiar variables in terms of x and y. We know that if we want to find our tangent line, we're going to gather our ordered pair and our slope. Ordered pairs are already provided for us in the problem. We know that's ordered pair 1, 2. Next up, we need to find the slope. So slope comes from dy dx. So we take our ordered pair 1, 2, evaluate it into the derivative equation. So replace 1 with x, replace 2 in for y, and we get 1 times 2 cubed, which is going to be 8. So we have our ordered pair, we have our slope, and then point slope form. Okay, part B. Use the tangent line equation from part A to approximate f of 1.1. So I'm going to solve for y. Once I get my equation where y is by itself, I'm going to replace x with 1.1, and that will allow me to do linear approximation. Okay, so linear approximation, solve for y. I added the 2 over to the right side, and then I just simply plugged in my decimal and for x. So 8 times 1.1 minus 2 plus 2 gives me 2.8. Okay, so the next part says, given that f of x is greater than 0, so that means the y value is greater than 0, and x is somewhere between 1 and 1.1. So basically, this is telling us both x and y are positive, right? So if both x and y are positive, okay, just keep that in mind. It says, is the approximation for f of 1.1 greater than or less than f of 1.1? Okay, so what we're going to do is we're going to figure out what the second derivative value is, or what conclusion can we make about the second derivative value, because that's going to help us out in terms of determining whether our tangent line is an over approximation or an under approximation. So if we know that x and y are both positives, then if I were to evaluate the second derivative function, if y is always positive and x is always positive, then there's no chance that this expression can ever be negative, right? And if this is always positive, that means my second derivative is positive, which is concave up. Okay, so that's what we're trying to get to. If we know that the graph is concave up, then we have our entryway into figuring out this answer. Since our graph is concave up, linear approximation is going to under approximate the value on the curve. Okay, it's going to be below the curve. So therefore, we know that 2.8, this linear approximation, is going to be lower than the actual 1.1 on the curve. Okay, so that's the conclusion we need to be able to connect to. The fact that this information tells us that there's no chance this can ever be negative, which means that the second derivative value is always positive. If it's positive, we make the connection that it's concave up. If it's concave up, a linear graph is going to end up sitting below. Therefore, our linear approximation is under the curve. All right, part C. Find the particular solution for y equals f of x. So we're going to solve this differential equation. All right, so first up, I'm going to write the equation here. I'm going to get this to be a clear fraction here. So I'll put that xy cubed over 1. And now I'm going to cross multiply. So as I cross multiply, I can get my dy and dx in the right slots. And now I can decide, do I have full separation? So I want y's on the left, x's on the right. So I have one thing out of place. That's y cubed needs to be divided over to the left side. So I'll divide the y cubed over. And this is where we are. Okay, so once we've gathered y is on the left, x is on the right, we can take the antiderivative. But if we take the antiderivative, we also have to understand that y is not going to stay in the denominator because we have to bring this up and apply power rule. Right? The only time we can leave a variable in the denominator and use natural log if it's y to the first power. If it's y to any other power, we have to bring it up and go through power rule. So I'm going to bring that y back up to the numerator and set it up for my antiderivative rule. Both sides is going to require power rule. Okay, so y to the -3 becomes y to the -2 over -2, right? We add 1 to the exponent. Same here, we add 1 to the exponent. So we get y to the -2 over -2 equals x squared over 2 plus c. And once I'm here, I'm just looking for ways to clean up my left side if I can. So I see the -2 here. If I can just multiply everything through by -2, I can shift any unnecessary terms from the left to the right side. I'm just anytime I can do some cleanup on the left side, I'm going to take advantage of that. Okay, so I'm left with y to the -2 equals -x squared plus c. I'm multiplying everything through by -2. The -2 times c is just still going to be a constant, so I'm just leaving that as a plus c. And just a little bit more cleanup here. I'm going to make that 1 over y squared. So this is not going to clean up very nice at this point. If I were to continue to solve for y first before plugging in my order pair, eventually I'm going to have to come across plus or minus square root, and I just feel like it's a little bit cleaner and easier to solve for c at this point rather than waiting a little bit later when the square root is going to show up. So I'm just going to go ahead and enter in my order pair, 1 for x, 2 in for y, and see if I can solve for c. So I get 1/4 is equal to -1 plus c. I add 1 to both sides. 1/4 plus 4 over 4 is 5/4, so c equals 5/4. So now I know that my c value is 5/4. I will replace my c with 5/4 and see if I can make my way to solving for y. Okay, so from here, I'm able to update my general to a specific solution. I get 1 over y squared equals -x squared plus 5/4. I would like to get that y squared flipped, but I think it's a little bit cleaner if I can get this right side to be 1 fraction. So I'm going to find a common denominator of 4, and I can make this -4x squared over 4 plus 5/4. And now I'm down to a fraction equaling to a fraction. So this is what I can do here. I'm going to flip this fraction here. I'll make this y squared over 1. And if I flip this fraction, I can flip this fraction as well. I'm just doing whatever operation on this side as I'm doing to the other side. So I'm going to flip this side and flip this side. And that gives me y squared is equal to 4 over -4x squared plus 5. And now the only thing left for me to do is to take the square roots. So as I take the square root, I get y is equal to plus or minus square root of 4 over 5 minus 4x squared. Now, we know that anytime we're dealing with solving differential equations and we're having to choose between plus or minus, the way we decide is we look at the y value, right? Whatever the sign of the y value is going to be the sign of our equation, right? But we only need to do that if we're having to decide between plus or minus of the square root. So we have a +2, so therefore we want a positive square root. So I just decided to clean this up a little bit. Square root of 4 over square root of 5 minus 4x squared. I can clean that square root of 4 to just be 2, but the denominator is not going to clean up, so I'll leave that square root in the denominator. It's okay to leave radicals in the denominator, and we can just leave this as our final answer.